It is our privilege this week for the 1W-MINDS seminar to have Wotao Yin here to talk to us. He is the director of the Decision Intelligence Lab at Alibaba Damo Academy, having recently left UCLA 29 days ago, I guess, according to recent updates, where he was a professor in the math department. He is a prolific and extremely well-cited expert on optimization, signal processing, and mathematical data science more generally. And we're really happy to have him here to tell us what he's been up to recently. So I'll turn things over to you, Wotao.
All right, thank you so much. Thank you for the introduction, and also thank you all the organizers to put up this nice series since April last year. There are lots of wonderful talks, and to facilitate exchange of ideas. Also, maintaining this website is a great amount of work. I really like going to the website. So it's my greatest honor to come to here and give a talk here today. And this is about a paradigm change in optimization. And this talk will be based on essentially a couple of papers, and I'll focus on the high-level ideas, skipping some of the technical details, but let me just mention some important names. So there's a survey paper that we put up online in March and recently updated, and it was done by a group of people at UT Austin in Zhang Wang's group, and a couple of folks at UCLA, including myself. And the second part of this talk will focus more on a fixed point network. It's part of the revolution of learning to optimize, which I really like. And these are all recent work, like 3 months old. It was done mainly by people at UCLA. And recently, Samuel Wu-Fang has moved to Colorado School of Mines. I think a couple of folks here are in the audience, so they can also help answer questions. All the numerical results presented are open source codes for you to reproduce if you wish on GitHub. Okay, so first of all, background. So learning to optimize certainly combines machine learning and optimization. So let's first do a quick overview of machine learning. Machine learning, roughly speaking, answers are given as existing data. You use those data to train machine learning model to give answers, to give very good and quick answers in the future. This is a form of induction. Optimization, at least traditional optimization, does not need any correct answers to begin with. However, it requires you to specify how to evaluate the answers by specifying the constraints, by specifying the objective functions or other optimality conditions. And then, calling optimization algorithm, you get the answers that according to the evaluations. So there are methods essentially giving answers in different ways. Optimization is more like a prescription. So learning to optimize use previous optimization experience, previous data of optimization to either get a faster optimizer or an optimizer that produce better solutions, in short. So this certainly is a paradigm changing optimization. Traditionally, in classic optimization, the methods are typically hand-built by experts. They know theory and they know benchmarks, and so they come up with methods that have convergence guarantees and perform pretty well on benchmarks. And those methods usually written in a few lines, and they are essentially built from a handful of basic components, such as gradient descent, conjugate gradient, Newton or quasi-Newton steps, and so on. When it comes to applying applying an optimization method in an application, the user is going to pick a method that's suitable for their problem, and then perhaps maybe tune some step size, tune a few parameters, and they solve the problem. So this is classic optimization, and the design of the optimizers is usually not the user's responsibility, it's the expert's responsibility. Learning to optimize somehow involves users in the design of the optimization algorithms. So the user can significantly improve optimization performance by using training based on data. So the user first needs to select a template of the optimizer with the tunable parameters. And then the user needs to collect a set of optimization problems, which we call optimizees, that represent the problem she or he gonna solve. And then using this training process to improve the parameters, improve tunable parameters. Once it comes to online application, it just applies the learned method to new but similar optimization problems. So it's basically training involved. Now, not all application or settings are a good fit of learning to optimize. Only some of them do. So at a high level, you can summarize like 2 different settings where you want to consider learning to optimize. In the first setting, you have many samples of good solutions, but it is hard to write down a very good optimization model, an analytic model, either because it's hard to get the solution you want, or to get the solution you want, you have to come up with non-convex or some terms that are difficult to optimize. So here you want to use learning to optimize, give some options to learning to optimize, and let learning to optimize figure out a model that can produce a better solution. In a different scenario where you still have many samples of good solutions, and you're going to repeatedly solve the same problem. Every problem is going to have new data, but it has the same structure, similar size, or otherwise, for example, similar sparsity pattern. So here you want to ask learning to optimize to find a quick way or faster way to get to the solution. Not necessarily a better solution, it could be the same solution, but just faster. So learning to optimize is used to find essentially a fast shortcut. So one, improve the solution, the other to make the solution faster. Now to make things more concrete, let's use gradient descent as an example. Let's consider minimizing a smooth function. And instead of using a fixed step size, using a gradient at the current latest iterate, you can use all the iterates so far and all the gradients evaluate at the previous iterates. And then use a mapping, train a mapping, which is parameterized by theta to combine all those information to generate a new point. For example, G can be a linear combination where this phi can be the coefficients. And this paper about 5 years ago from NeurIPS formulates this particular problem. It says, please find a combination of the previous information specified by phi, dictated by phi, such that the sequence of the points produced from iteration 1 to t will have a small weighted average of the objective. So smaller weighted average means faster convergence in terms of objective values. And such good performance should be obtained on a set of objective functions. So in short, the problem is to find how to combine existing information such that t-step, a fixed step of minimization performance, is optimized over a set of problems you're going to consider. And this was applied to machine learning training. So the title of the paper is actually easy to remember. It's called Learn to Learn by Gradient Descent by Gradient Descent. So the outer gradient descent is that they actually actually update this parameter theta by stochastic gradient. Okay, so this G obviously is important, is the template of L2O. It has to come from somewhere. Roughly speaking, there are two classes of methods. The first class of method creates G based on existing optimization methods, or use existing optimization methods as a start point. It often searches for best combination of the previous evaluation, function evaluation, iterates or gradients, or maybe some information, some second order information. So the benefits of this method, or strength of this method, is easier, relatively easier to interpret, and in some cases you can even come up with theoretical guarantees, or show that there exists such a great combination for the set of problems you want to consider. And for this set of problems, for this set of approach, we call it model-based. There's an optimization model at the starting point. Machine learning folks, deep learning folks, also consider universal approximators. They create a multi-layer neural networks, often recurrent RNNs, and use the entire RNN as the optimization method. So they often discover completely new methods without referring or resembling any of the existing methods. And this class of methods usually competes really well in non-convex optimization, especially on those non-convex optimization where there's not much pattern. But they're not so competitive for inverse problems or for convex optimization, because their performance usually is not robust. So what I'm going to do is spend about 5 minutes to mention some basic techniques in model-free world, and then spend the rest of the time on model-based methods. Okay, so almost all model-based, almost all model-free methods are based on RNN, which is a class of neural networks that recurrently applies to a sequence. So on the left is a cell, is one single cell of RNN. The parameters are U, W, and V. The input is X, the output is O. And when you apply it to optimization algorithm to generate a sequence, you unfold it. So the information gets passed from one layer to the next layer, but the U and W and V stay the same. So here X actually represents the current point, some of the previous iterates, the local gradient and other information about the function, the grid, and constraints. The O actually represents the new iterate. So U, V, W as parameters to learn. But there are many issues of RNN, well known. And those many issues are addressed by LSTM, which is essentially a extended, more generalized cell that allows you to add and remove information in certain ways. So roughly speaking, LSTM provides more tuning knobs. Most of the existing L2O learning to optimize model framework is based on LSTM. I'll list a few. And I just present a paper where every row, every line in the table corresponds to one work. And the references of these works are in our survey paper. I won't mention each work, but I just mention some common pattern. Now, first of all, people are basically taken techniques to model sequences in the deep learning here to generate optimization sequence. So for example, when you process a sentence or like a few sentences, it's basically a sequence of words. Now you take the technique to generate a sequence of iterates in optimization. So there's an analogy here. But there are some adaptations done for optimization. First of all, the training objectives are pretty diverse. They use objective function, you use constraint violations, they use KKT conditions, and in some cases you can also first generate the true solution and then train according to the true distance to the true solution. There are various kinds. And then secondary, some other techniques involving, for example, scaling. In optimization, when you rescale the problem, it's the same problem, it doesn't change the solution. So you expect the method still work on the rescaled problem. So this motivates data augmentation. So when you have a set of training examples, you can rescale the training examples, generate more training examples. So therefore, make the method more robust. So like mentioned before, model-free L2 is mainly competitive in non-convex optimization. It lacks the guarantees in convex optimization and in some of the inverse problems. And a common challenge in these LSTM or IN-based approach is the length of the iteration or the depth of the network. So you must decide before you start training, you must decide on the unfolding length of the network. If the network is deep, has many layers, then it just has a higher memory cost and also become much more difficult to train. If the network is very shallow, then it's easier to train, but using so few layers or so few iterations may not produce a solution that has the accuracy you need. So you might want to do more iterations. So there's this trade-off here. Here are some numerical results we had. We took the learning to learn by gradient descent paper. We used that network, and then we tried a different length. The length is called Unroll. It's either 5, 20, or 100. And here's an example where with 5 layers, the training very quickly converge. But it takes much longer time to train deeper neural networks. This is well known. However, using this trained 5-layer neural network on testing problems, on optimization problems, you're going to see, well, in the first 5 steps, the network perform really well. It decreases the loss. However, after 5 iterations, if you keep applying, keep expanding this LSTM, the performance gets worse, and even worse than the initial point. This difficulty can be somewhat alleviated using something called curriculum training. You essentially train a network, train a 5-layer neural network such that it not only perform well on the initial point, but also perform well on the point generated by the network itself. But that does not solve the problem, does not generate guarantees. It just have slightly better, you can go slightly better in depth. By far, I think this is the major problem in optimization. In optimization, even if we have to do, it's very common that we run a method 100 of iterations, even thousands of iterations. We can't just always rely on like 5 iterations to produce good solutions. So that needs, in other words, that needs model-based L2. Many of the approaches in model-based L2 can run a large number of iterations. And this is the focus of this talk. The first technique in this model-based world is this unrolling. It's essentially a L2 method based on existing iterative method. And this is also one of the earliest L2 method by Gregor and LeCun about 10 years ago. I use LASSO as an example, where you minimize a least squares loss plus L1 penalty. One of the most common method is this iterative shrinkage and thresholding algorithm, where you take gradient descent and then you do a prox with respect to L1, which is shrinkage. So this step reduces the least squares loss, and this step reduces the L1 loss. And when you reach a fixed point, you can show it is the solution to this model. So introduce this W1, W2 matrices as such, and introduce theta as a parameter. you can write this iterate as in this form, which resembles a little one cell of a neural network. Greg and LeCun's idea is to first iterate this cell for k times. K is fixed, and then every time when you iterate the cell, you're free to choose a different set of parameters, W1, W2, and theta. And then you use data. You use true optimization method to come up with the inputs and outputs, and use those input and output pairs to train all these parameters. And they obtained great results. At the end, you apply this k-layer neural network to new problems. You can very quickly find solutions. And usually their k is just a 16 or 20, a small number. So this iteration, this kind of network is called unrolling. You unroll existing iterations. And you can do this not just to LASSO, you can do that to many other problems. And there have been many examples in inverse problems, in PDEs, and also using graphical models. The drawback is the number of free parameters. So there has been a series of work by my group and by others where we realize W1 and W2 don't have to be separately learned. You can tie them up. And then across the layers, you can make these different W's the same. It does not lose performance. And then later on, we even find there are analytic ways to pick W using the idea of coherence. We minimize coherence between W and the sensing matrix A, and that come up with a W that competes really well with the data-driven, data-trained W. So at the end, it boils down to actually choosing this set of thresholding parameters. You might want to threshold more aggressively initially, and then gradually let it converge to the original value. So anyway, I think unrolling is pretty successful on specific topics, specific set of problems. But it has challenges. The first challenge is unroll length. Still, all layers has better performance, but it becomes difficult to train. And then what about performance guarantees? Only on very narrow cases. For example, fixed size of matrix A, and when matrix A has good RIP property, can we prove that there exists at least a set of parameters such that this neural network, for example, has a linear convergence, which is better than existing optimization guarantees say. And then another issue is, what if you train for k iterations and you cannot stop there? You're not satisfied with the accuracy, and what can you run more iterations? Or what if you apply this trained L2 network to problems out of the distribution that you trained on? So this can be partially addressed with this technique we call safeguarding. It's a simple idea, although there are some technical challenges to address. So this idea came up by Howard Heaton, and in the paper, in the ICLR paper a year ago. So you basically come up with energy E such that if XK sequence converges to a solution, then the energy sequence should also converge to a minima, that at least converges to a non-negative number. And when XK does not converge, or does not converge for long, for enough number of iterations, and this condition will be violated eventually, where you can switch to a classic update. Let's say switch to this ISTA classic update. But you must make sure that mixing up the descent, the monotonic descent, and classic update should still guarantee convergence in a theoretical way. So that means you have to choose T and this E using classic optimization techniques. And also, learning to optimize updates, these L2O updates, may not always decrease any energy, because it has its own way to shortcut the progress, right? To find the shortcut. So it may not monotonically decrease objective, may not monotonically decrease any KKD condition or other optimality measure. So you must allow periodic increase in certain energy to occur. So that limits the choice of this energy. So we ended up using operator splitting frameworks, using monotone operator theory to come up with, for example, a series of forward backward and Douglas Rushford or ADMM kind operators that we can use as T. And then we use non-monotone line search technique, motivated by non-monotone line search technique, to come up with an energy that considers the history. So anyway, there's some technicalities, but this thing actually works really well. So let me show you some numerical examples of unrolling. And we use still just the LASSO example, where Q X star is the true sparse signal. A is a fixed matrix. A represents a sensing modality. For example, the how signals are sensed or acquired in a MRI machine. And we used such BQ and XQ star pairs to train a neural network using the squared L2 loss, the true signal. And we fixed K to 16. And we tested tested recovering the signal in different cases. No noise, with some noise. When A is ill conditioned, barely satisfy the RIP property, or the problem is has a quadruple size. And we compared the original Greger-LeCun and a sequence of improvements that we did, as well as a AMP message passing based learned optimum algorithm by I think by Borgadin at Ohio State, and an analytic method where part of the W is actually obtained by a separate optimization problem rather than trained. And finally, this gated lista by Wu and his colleagues from Tsinghua. So the comparison is inconclusive. There's no single one that always performs really well. The green one, A-lista, is good in 3 out of the 4 cases. The G-lista is also good in 3 out of the 4 cases. But the message is, if you look, it's only 16 iterations. When you apply something for fixing 16 iterations, is really quick. And it's also almost instantaneous. Whereas traditional algorithms like ADMM or lista or FISTA needs hundreds of iterations to converge to this kind of accuracy. So when you take a signal from this distribution, you have trained on, it performs really well. Now, however, when you take signals outside the iteration, outside the distribution, you need safeguards. So here we're comparing some methods that people used in training neural networks compared to some L2O enhanced methods compared to traditional gradient descent, the network of accelerated, essentially network of accelerated gradient descent, as well as the lista. So after 16 iterations, you no longer have neural networks to apply. So the dashed lines means you basically fall back automatically to the traditional method. The good thing is ESTA is warm startable. So you can start from where it is and still going to converge. And so these are essentially ESTA iteration started from where lista is left at. And you see the purple curve catch up, and this purple curve is actually the network of acceleration. This is one by Beck and Taboo. And many of the other ones just don't work. And these L2O dash are model-free methods. They're neural network-based methods. They just don't work. They don't even converge. And if you use just these gradient-based or accelerated gradient-based methods from deep learning on this particular problem, it just don't converge really well. So this basically shows that if you want to have robustness, you will have to combine learned method with traditional methods. So this is just a larger problem. We come up with this, we get similar conclusions. So this is unrolling an existing method and to train the tunable parameters. A better technique is called plug and play, and it allows you to plug in a trained operator and iterate for infinite number of iterations and still have guarantees. So here's the background. Consider a data fidelity term plus a regularization term, gamma is the parameter. Suppose we apply ADMM. Then it can be, on this particular problem, you can write it down in a very compact form, where this step reduces G, this step reduces F, and they produce different primal iterates, and then the dual update essentially will make X close to Y, make them equal eventually. Okay, now using, let's say, if you apply this model to imaging, to some inverse problem, then this step means take a noisy image and produce a less noisy image. And the second step means you improve the consistency. However, not all the good image denoisers can be written as a proxima of some function, let alone proxima of a convex function. The state-of-the-art denoisers, at least 5 years ago, were non-local mean, EM3D, block matching 3D filter, as well as a trained CNN-based denoisers. So the idea is to replace the prox G step by these operator, which in some sense does the same thing, take a noisy image and produce a less noisy image. So Wotao Krishnan, about 6 years ago, well, 7 years ago, was doing an internship at Los Alamos National Lab in Brent Warburg's group. And they come up with this heuristic where they just replace prox G by a nonlinear operator. And they experimented and get really good results. And this idea has been picked up by researchers like Sandy Chen at Purdue and applied it to other inverse problems. And a set of other inverse problems, this is one of them, and they get great results. So imagine there's a clean image and you downsample it. You want to recover the original clean image. This is called super resolution. They compare it to a bunch of other methods I won't mention, and they simply plug in this BM3D operator into this ADMM framework, and they get much better results. And they have a set of other numerical examples, always produce better results in plug and play. And then people start to think, can we get guarantees? So about 2 years ago, Ernest Rhee in my group and the colleagues at Texas A&M came up with this guarantee. Well, he says, first of all, you can definitely use a infinite depth. Unrolling length is no longer an issue. You can stop whenever you want. And then there's a guarantee under the assumptions that F is strongly convex, which is a little bit restrictive. And this denoiser, which is more important, is close to identity. And if this denoiser needs to be trained, then you can use spectral normalization during training to enforce this condition. So, so this basically tells you it won't diverge, it won't produce unreasonable results. However, it is difficult. First of all, you have to train a denoiser before you plug it in. You plug it into the ADMM or other operator splitting algorithms. So in other words, the training is not end-to-end. You often may have to train this denoiser on some other set of images where you have the clean samples, rather than on the sensor data and final image in the end-to-end fashion. So it's no end-to-end training. The second one is somehow the theorem only says convergence, doesn't explain why the fixed point is a good image. It is a better image than say total variation minimization. Nonetheless, it doesn't explain why the image is good, because the training is not end to end. So this problem was again addressed by the stiff equilibrium network, which appeared about 3 years ago. And in this network, you can train end to end. You can also have infinite depths, and there's ways to address the training issues, training difficulties. So we started with neural ODEs, which essentially plugging a black box ODE solver into the neural network as one layer. And then later on, these people generalize the methods, and then they say, in theory, you can apply a operator infinitely often, and then output the fixed point of the operator. So the layer is essentially an operator, is a fixed point operator rather than a set of explicit operators. Now, let me give you an example. Compare explicit network with a fixed point network. I took this image out of one of our papers. So the input is D. The D first goes through a operator Q parameterized by theta. It usually extracts the features. In the traditional explicit network, you feed the results, feed the output of Q theta to another set of layers. For example, does classification and generates the label Y. Now, in the implicit network, there's a fixed point operator here. So you take the output of Q, and then you have to solve a fixed point equation. You get the fixed point U theta, U star, and then feed U star to the classifier. So this is explicit. This is also called equilibrium. And although you can explicitly write down R theta, you cannot explicitly, often you cannot explicitly write down the fixed point operator that maps the input U to U star. In practice, you can, of course, you cannot solve it exactly. You can either, if you have a contraction for some theta, you have contraction, you can iterate this contraction for finite number of steps, or you can use other algorithm, ODE or optimization methods to come up with an approximate solution. And there's operator splitting version of that. So in other words, R theta can include both the physical part corresponding to the sensing modality as well as parameterize the regularizer. And this was independently done by my group and Gilton et al. From Rebecca Witt's group. Okay, so let me address one important issue with backpropagation. So to update this parameter theta, we have to compute the gradient of the training loss with respect to the parameter. So an efficient way is to do backpropagation. So that is the chain rule through applying the chain rule through the layers backward. And you're gonna hit this fixed point layer. Introduce a notation T theta. The T theta take the original input as well as the feature extraction layer and define the fixed point of T theta as U tilde. So this U tilde depends both on D, the input, and the theta, which is the parameter of the operator. So now in the network, there's this layer that takes D and generates a fixed point, where the fixed point is implicit. To do backpropagation, let's define the Jacobian matrix, which is identity minus the differentiation of T theta with respect to U. Now this is explicit, and this thing exists almost everywhere as long as T theta is Lipschitz and T theta is contraction for every D. It's contraction with respect to U for each D. And when we differentiate the output, the fixed point output with respect to the parameter, the formula, this formula, you can differentiate with respect to theta on both sides. You get this. So it gives you the differentiation of t theta with respect to its first input, and then the once again the fixed point differentiation with respect to theta, and plus the differentiation of t theta with respect to theta itself. And then assuming this inverse exists under these conditions, well, under this condition, the inverse does exist, and then just compute this Jacobian and its inverse, you get this differentiation, and you can plug this one into the backpropagation chain rule, and you can update theta. So on the downside, on the upside, well, you essentially turn an infinite layer to a finite computation, finite storage and finite computation. On the downside, we still need to form the Jacobian matrix and also compute its inverse, which is relatively expensive, especially consider you have to do this for a small mini batch every time. So Howard, about 3 months ago, realized you don't have to generate Jacobian matrix at all. You just apply the same formula without the inverse of the Jacobian. And under essentially the same set of conditions, you can show that the resulting gradient is a still descent direction. Right? It's not the steepest descent direction. Nonetheless, it's a descent direction. And it works really well. It gives you a huge speed up. It also allows you to handle complicated t theta, for example, those from ADMM. Let me compare the 3 neural networks that involves a optimization operator t theta. When you apply the t theta in a feed forward, when you evaluate the fixed point, you take the input d, you choose a initial point, for example, 0 vector, and then you apply t theta for k steps. Now, the traditional unrolling approach will backpropagate in the traditional way, although it allows you to have the freedom of choosing different theta for every step. The equilibrium or Jacobian-based approach used the inverse theorem, inverse mapping theorem, and essentially come up with a formula that skip all the middle steps and use inverse Jacobian to differentiate with respect to the input, jump to the input. So our approach says you just backpropagate one step. It's sufficient. It's enough. And it comes with a proof. So here's the numerical results. I'll give you the setting on the next slide. So we're comparing this Jacobian-free method with the Jacobian-based method. On the left is number of epochs, on the right is the time, and this is test accuracy. So it's surprising to us. We initially thought, hey, we're not using accurate gradient. We used to use a descent direction. We would slow things down in terms of epoch. It's not the case, surprisingly. We don't know the full reason yet. So it takes fewer number of epochs to reach a good test accuracy than Jacobian-based or those equilibrium-based work. And of course, it also takes fewer time. So we test them actually on traditional classification results. We thought, of course, you can do it on optimization. Nonetheless, we did it on compare it to other neural networks on classification, which is more traditional. We recognize handwriting digits as well as more complicated images. We compare it to explicit networks, compare it to neural ODEs, because neural ODE, those papers did this test too. To augmented neural ODEs and compare it to this monotone operator network. And we were able to use a smaller step size and use the fixed point and do simple backprop and to achieve a higher accuracy in shorter time. And on the CIFA 10 example, we tried to compete with ResNet to achieve a accuracy within the 93% range, which is the golden standard. If you can achieve like a 93.7, it's actually considered very competitive. And this is done without using very advanced techniques. We put a star there means that we actually did data augmentation. When you train on the images, you also rotate the images, scale the images, etc. The standard data augmentation techniques. We're be able to use the same number of parameters to achieve higher accuracy. So basically, it says this implicit layer has a stronger expressibility, and it's also easy to train. We have a bunch of other numerical examples, but I want to use the last 10 minutes to show you something that's actually a little sophisticated. We want to do a inverse contextual game using fixed point network. So here, the D is a vector represents the contextual information, like how the payoff is set and how constraints are set. So D is given and known to all the players. However, we don't really know the strategy of all the players. We can only observe how they play. So we wish to predict the game outcome without knowing individual players, but knowing only the contextual information. Okay, and so this requires some Nash equilibrium setup, which translate the problem into a mass formulation. So we have K self-interested players, selfish players, and each one of them has a payoff function given its action as well as the action of other players and given the context information. A Nash equilibrium is basically a set of actions where no player can unilaterally improve their payoff. We model this. I'll skip the details. We model this as a fixed point, where F is called payoff gradient or gain gradient. C is the set that constrains the payoff player's actions. For example, if the strategy is probability strategy, C is the probability simplex. There are cases where you have multiple constraints. You can use the operator splitting. I won't go into details. So here's an interesting example. Suppose D decides a payoff matrix. So W are I think W is unknown. D is given. Okay, so we do not know players' payoffs, but we know it depends on this common context information D. And there are two players playing this game, and we generate a set of training data and observe how they play and how they reach equilibrium. And then we use a neural network, two-layer neural network with 500 parameters to represent this game gradient. The once we train the game gradient, we can either predict the outcome of the game, or we can of the two players, or we can keep one player and let the other player be driven by the trained gradient and play with the existing player. So optimal is the player that knows this information, knows this true information. Uniform means a certain probability choosing rock, paper, and scissors. And red is the player driven by our trained game gradient, and optimal is the true. It's like a two player both know their true strategy, the true payoff, and compete each other. So you can say the red performance is awfully close to the optimal performance. And we also did it. And this is, I think, an idea from Daniel Kenzie. We also did it on traffic simulation. So traffic is a game because every driver is presumably selfish. I want to minimize their commute time. The context is the road condition, which is decided by weather, road work, and others. And the Nash equilibrium on a given road network can be calculated analytically. And then we train or use 3 layer fully connected neural network to represent the game gradient. And we have two set of constraints. The one set of constraints is the road network constraints, flow in equals to flow out. And the other is the sum of the roads are one way. So there's a non-activity constraints. And because of their two set of constraints, they're incompatible. Computationally, we use three operator splitting. And the goal is to predict, given the D, predict the road condition. Now that, once you've given that prediction, you can tell a new user, new driver, which road to take. You can also use the prediction, give the prediction to the road management. Let them decide, let them simulate the road condition and decide when to do certain road work. And this is numerical results. We're comparing the L2O solution to the analytic solution. And this is a percentage of the road segments where the prediction is sufficiently close over the total number of road segments. So this one is better if it's close to 1. And we did it on actually 5 cities parts using a real network and simulated the traffic conditions. And you can see that over 95% of the time, the traffic on the road segments are well predicted. So this is I think this is really good results. So I'm running out of time, and let me summarize. So learning to optimize is new paradigm. It reduces the design burden on expert and let users to choose some kind of learning template, optimization template, and use their examples to train the parameter, decide the final algorithm. It's very useful. Hopefully I demonstrated it's useful to come up with better solutions or come up with faster solutions. So fixed point network is the latest evolution in this. The fixed point network is one of the latest work in this evolution. It's flexible, it allows you to train end-to-end, and the training performance is also very good because you don't even have to come up with the Jacobian matrix or invert it. The good performance is observed. It's still a fast evolving field. And I just mentioned that I have left many topics uncovered, including the L2O methods for discrete and combinatorial or mixed integer programming problems. I did not cover any reinforcement learning. I did not cover meta learning, which includes learning to optimize as a subfield. Many things are not covered, but I just say, this is a very exciting field. Even on traditional optimization, it's already sees much of progress. So thank you. I'll stop here.